Okay, so first video, 1-3, determining limits analytically. Recall our limit as x approaches c of a function equals L if, of course, the limit exists. So we looked at graphically determining a limit, numerically, which I said we don't study a whole lot more after this chapter. And now we're going to look at determining limits analytically, and that's using calculus and other algebra techniques. Okay, so first things first, attempt direct substitution always. The limit as x approaches c of a function will be equal to the value of that function as long as c is in the domain of the function. Okay, what does this mean? So determine each limit. The limit as x approaches 4 of the absolute value of x. Using the direct substitution method, we just take the value of c and plug it into the given function. Square root of 4 is 2, so the limit exists and the limit has a value of 2. Now the square root of x, we know that that domain is x is greater than or equal to 0. So if I asked you for the limit as x approaches -2 of the same function, that couldn't exist because -2 is not in the domain of square root of x. Limit as x approaches 3 of the absolute value of x minus 3. The domain of the absolute value function is all real numbers, so I'll be able just to plug 3 into the function, and the limit is therefore 0. Limit as x approaches -2 of -1. Okay, now remember what this statement means. As x approaches -2, on the graph of the function, f of x equals -1. If we think about what this looks like graphically, it's just a horizontal line through -1. So no matter where we are in the domain, no matter what x is equal to, y always has a value of -1. So that limit will never change no matter what the value of c is. Alright, limit as x approaches -8 of the cube root of x. Now the cube root has a domain of all real numbers, so we can use direct substitution for this as well. Cube root of -8 is -2, so that's the value of the limit. Alright, how about the limit as x approaches 1 of x plus 3 all over x minus 1. Direct substitution gives us 4 over 0. We can't divide by 0, so this limit does not exist. We will discuss in more detail what this represents graphically, but if you look at this rational function, the domain is that x cannot equal 1. That's the only restriction. So graphically, a vertical asymptote exists at the line x is equal to 1. Your homework tonight, or for our next class, numbers 1 through 43 odd, deal strictly with using direct substitution to determine a limit. I am going to continue and have the following notes for our next class, but your homework only goes through direct substitution. Okay, so what if you were asked to determine the limit as x approaches 0, square root of x plus 1 minus 1 divided by x. Direct substitution, when I plug 0 in my numerator, I get 1 minus 1 all over 0. So direct substitution gives me the form 0 over 0. Now we can't divide by 0, but this form here does not necessarily mean that the limit does not exist. Number over 0 is very different than 0 over 0 on a direct substitution. So let's talk more about that. Indeterminate form is the form that exists when direct substitution results in 0 over 0. That doesn't mean the limit does not exist. The limit could exist for the value that we plugged in, or the limit might not exist for the value. We just need to do something more to determine the answer. So analytically, what are the algebra techniques we can use? For the function, possibly we can factor the function, we can rationalize the numerator or denominator, we could graph it. I have this in all caps. 0 over 0 means do something to the function. Don't just leave it and tell me that the limit doesn't exist. 0 over 0 graphically represents some type of discontinuity on the graph. It can be a hole or a jump, but we know that something's going to happen on the graph at whatever value gave us 0 over 0. Now, number over 0 graphically represents a vertical asymptote. So they do tell us different things about the graph of a function. Okay, so let's look at this simplifying indeterminate forms. We'll go back to, start with an easy one. Limit as x approaches 3 of x minus 3 all over x squared minus 4x plus 3. Direct substitution, 0 on the top. 9 minus 12, negative 3 plus 3 gives me a 0 on the bottom as well. So indeterminate form means you have some type of algebra technique to simplify the original. This is what your quiz was on. So if I factor the denominator, factors of 3 that add to negative 4, that's my factor denominator. Now these factors will cancel, and my resulting function, 1 over x minus 1, when I do a direct substitution, I get a value of 1/4. Now think about our notes from section 1-2. The existence of the function, so f of 3 doesn't exist because direct substitution didn't give us a real value. But the limit of the function still exists. Remember that we don't need 1 in order for the other to exist. Now graphically, what would this look like? This is the function we started with, and we were able to simplify it to 1 over x minus 1. So the domain of that function, x can't be equal to 1. That would be a vertical asymptote on the graph of the function. I know that f of 3 doesn't exist, and furthermore, what would the y value be at 3? That's the value of the limit. So the hole on the graph exists at the point 3, 1/4. So 3 1/4 is where the hole would be. Now let's talk about the parent function here. The parent function is 1 over x. So I maintain what that parent function looks like, now just shifting the vertical asymptote to the right 1 unit and then having the hole here at the point 3 1/4. Now on a graphing calculator, unless you looked at the table of values, you wouldn't be able to see that that hole exists. So that is important because it stems from the domain of the original function. X can't be equal to 3, x can't be equal to 1. And we'll talk about the different types of discontinuities next. Alright, limit as x approaches 9, x minus 9 all over square root of x minus 3. Direct substitution gives me 0 over 0. Now when I look at this isn't a problem where I'm going to factor it, but I see a square root. So our technique there would be to rationalize. Now if you remember from advanced algebra and pre-calc, we use the conjugate of the denominator. Sorry, these are running on top of each other. So I'm going to multiply the top and bottom by the square root of x plus 3. Remember, you can't square the original because it's not an equation. So in order to maintain or to keep the function the same, we're really just multiplying by a form of 1. So limit as x approaches 9. We will work on this in class. Do not expand the numerator. You'll end up making entirely too much work for yourself. Keep that in factored form. Now when I look at the conjugate, I only have to multiply the first and the last terms. Because if I use my first, outer, inner, last, those middle terms will always cancel each other out. That's how we get the square root out of the denominator. The x minus 9's now cancel, and it becomes a direct substitution of a problem for which 9's in the domain. Square root of 9 is 3. 3 plus 3 gives me a value of 6. Limit as x approaches 2 of x cubed minus 8 all over x minus 2. Direct substitution, 2 cubed is 8, minus 8 is 0, 2 minus 2 gives me 0. Okay, this is everybody's favorite factoring. Now as you practice, you'll see, if you get a resulting indeterminate form, it's a pretty good place to start, that there's going to be a factor that's the exact same as the denominator in the numerator. So let's talk about factoring cubes. So the first factor remains the exact same. And now the second factor looks a lot like a quadratic. It is a quadratic. It looks like the perfect square. Square the first, switch the sign of the original problem, find the product, and then square the last. So x cubed minus 8, how does that factor? Cube root of x cubed is x, cube root of 8 is 2. Square the first term, add the product, square the last term. These signs, the sign of the first factor and the first sign of the second factor, will always be opposite of each other. X minus 2 cancels, and now it's a direct substitution into the quadratic x squared plus 2x plus 4. And 4 times 3 gives me a limit of 12. Limit as x approaches 0, 4 plus x, quantity squared minus 16 all over x. Direct substitution of 0 gives me 16 squared minus 16 minus 16 is 0 over 0. Now when I look at this, I can't factor it, I can't rationalize it, and I'm certainly not going to expect you to graph this, but there's something algebraically you can do to the original. So what can we do? Expand that binomial. Square the first term, double the product, square the last term. So again, the shortcut, if I dare say, instead of writing it out as the product of two binomials every single time you're asked to do this, square the first term, 4 squared is 16, double the product, 4 times x, and then double that product, and then square the last term. Now notice these 16s will cancel. In the numerator, it becomes 8x plus x squared all divided by x. Common variable, I can factor out of everything. So now the function becomes limit as x approaches 0 of 8 plus x, and now direct substitution gives me a value of 8. Okay, we'll finish there, and we'll practice more of the finding limits analytically in class tomorrow. Have a nice day.